Good morning. I also want to thank the organizer for the kind invitation. In this talk, I will report some recent numerical simulation result of two-dimensional hard disk fluids. In detail, I will report the decay behavior of velocity autocorrelation function and also the decay behavior of energy carried autocorrelation function. And then I will discuss the mechanism of the hydrodynamic tails. And based on this understand to the mechanism, I will present a formula of velocity autocorrelation functions, which I mean it is uniform, which is suitable for the whole time period, and thus it bridges the kinetic range stage to the hydrodynamic stages. So, if I have time, I will discuss other topics. As a part of background, I would like to first introduce some previous focus of our group, our Xiamen group. You see, we have 4 faculties, and all of us here. But unfortunately, you see, my English is very poor, so I will speak slowly. Maybe you can read my talk instead hear what I say. So anyway, you can break me also to ask questions because my friends will help me answer your questions together. Okay. The problem we interested is how the autocorrelation function relax as a function of time in the statistical state. In particular, we want to know how the velocity autocorrelation function, how the velocity autocorrelation function decays, and how the energy carried autocorrelation function decays. This is important because if you obtain this kind of functions, you can calculate the transport coefficients following the Green-Kubo formula. And another interesting interesting problem is that how the density fluctuation relax. I mean, the mass density, heat density, and moment density. So this kind of study is also important because if we understand such a relaxed behavior, we can understand the relaxed behavior of hydrodynamic modes. And then you can understand the transport behaviors according to this behavior. But this topic is indeed interesting in all of us because it is a focus topic in non-equilibrium static physics. Indeed, our particular interesting, our particular focus is that the role of the asymmetric interparticle interactions will play. I mean, the role in determining the transport behaviors. Dr. He just introduced the concept of asymmetric particle interactions. Here is an example of one-dimensional lattice. The symmetric potential symmetric interaction means this kind, which can be described by this kind of potential, and asymmetric potential interaction can be described by this kind or this kind of potential. So the symmetry of the potential is important because you know the asymmetric particle interaction responsible for the thermal expansion. If there is no, in the case of symmetry potential, there is no thermal expansion. So that's a big difference you already know. And indeed, the problem we ask and have answer in the case of one-dimensional systems, which science for such a system, for such a one-dimensional system. In the case of asymmetric potential, the heat conduction, the energy carried will decay in this way, in this polar manner. And the index is 2/3 for asymmetric potential, and 0.5 for symmetric potential. So this question have the solution. But in our study, we do not want to challenge these predictions. We don't change the predictions of long-term behavior. We just want to emphasize the important difference in the transit period. I mean, in the beginning time, from 0 to a period. So our thing, the problem then is why the transit process is important. Then let me show such an example. This is autocorrelation function, the decay behavior autocorrelation function of the gas model, the two-dimensional hard disk model. I will show you detail later. And you see in the duality case, there is a first decay, there is an exponential decay, and then it tends to the polar decay. So this area is called canonical area or canonical stage, and this is the hydrodynamic region. So if this range is sufficiently long, if this rapid decay time is sufficiently long, then according to the Gromov formula, the contribution of the tail will be negligible, will be very small, because should be significantly small, because this part contribution the mind integrate. So in this case, the kinetic theory works well, and you can apply such as Boltzmann equation or Einstein formula to calculate the diffusion constant. And so I mean, the transit process is sufficiently important for physical applications. And yeah, sure. That depends the size. That depends how long the decay. So I will. That's what I will focus. Yeah. So so the transit process is sufficiently important in the gas model, in the study of duality fluids. So what about in the lattice case? Here I show some examples for lattice case. This is the correlation function of the energy correlation function and of the FQ beta model. This is a symmetric model with symmetric interactions. You see that it is really decay in a polar manner ever from the beginning of time. But for other asymmetric interaction models, such as LJ model and FQ, beta model, and other models, you find exponential-like decay in the beginning, in these regions. So I will not deny the possibility that the polar tail will appear in a very large time scale, but this time scale has already can guarantee a convergent thermal conductivity, practical, I mean. So in this case, I think the asymmetric interaction might be playing a key role to induce such a rapid decay of the autocorrelation function, and that's the reason why I return to the hard disk model. The hard disk fluid. Hard disk is a limited case of asymmetric potential, So, and this model has indeed been studied in very, very early times, and here is the details of the model we will study. We put disks in such cells, 10 times 10 cells, and the disk diameter is sigma, and in each cells, initially in each cells we just put one disks, so the particle density is 0.01. By varying the sigma, then you can control the density of the system. I mean the parking fraction, the parking fraction of the area function, which we will study as these three cases, which corresponding to the duality case and the moderate density case. And the temperature will be fixed at unit, and the periodic boundary condition will be applied. In previous theoretical studies, we have a lot of knowledge about this system. That is for the transient process. The kinetic theory predicts that there is an exponential decay stage, and the linear hydrodynamics predicts there is a polar T2 minus Y. And also the self-consistent modern coupling theory predicts that the tail should be this way. I mean, the logarithmic way, in such a way. So this should be they pronounce this should be appear in a very large time scale, and all these theories have been presented for many years ago, but the problem is we have not tested these predictions precisely. I mean, with conclusive numerical simulation result. Indeed, there are a lot of other questions, such as at this moment, it's still there is no uniform function to describe the whole process. I mean, these predictions are piecewise functions. So we need a global function to for the purpose of calculating the transport coefficients using the Kuba formula. And this gun just been attacked in this paper, just published several days ago, and but unfortunately, I think that this is a good work, but unfortunately, it applies a set of fitting parameters to obtain such a global function. So indeed, this kind of study has already done previously, but with different fit method. So fit parameter free formula is too absurd. The second problem is that I just have mentioned to validation the theoretical predictions. In this part, the most recent verification is published by this Japanese scientist, So in this work, at a low density case, the polar, the T2 minus 1 polar has been verified. I mean, in the case of velocity autocorrelation function. And also, for the first time, such a kind of decay behavior is also evidenced. But in their study, the amplitude of the predicted decay behavior have not been verified, not been discussed. This is their numerical result. In low density, it looks very like T2 minus 1, but moderate density divergence occurs. And fit this area, this covers, you can find almost the decay, the decay law of this polar form. Another problem is that to discuss the influence of the long-term tail on the observed values of transport coefficients. To discuss if this the time part changes as a function of such as density or temperature, and then how this tail part will contribute to the Gromov formula. So. Here is our result. We first need to confirm to find the minimum size for simulation, for conclusive, for reliable simulation size. Here is a result of using 2,500 particles, 2,500 disks, and you see in this case, you find a strong finite-size effect manifested by these oscillations. Even use 10,000 disks, you still find the strong or remarkable finite-size effect. So in this case, you cannot give a definite conclusion about the tail and particularly about the exact way of the decay. Until 15,000 particles, you obtain such a decay covers, and in this case, you can you obtain a time window by which you can fit the parameters. You can check the theoretical predictions. So, if you want to start this kind of problem, your system size should be large enough. As you know, in many previous studies, they just use 100 or 1,000 particles to do such a kind of things. The reliability should be revisited. And with such a confidence, I show the result. for the velocity autocorrelation function. For in the dilute case, you find the theoretical formulas as perfectly verified. Not only the T2 minus 1 low and also the amplitude. The amplitude is also agree with perfectly. And with the increase of the density, the situation is still good. But in the moderated density case, you see the obvious deviations from the T2 minus low take place. And indeed, in this time, the tail can be described by this decay law in this way. So the zeta is the viscosity coefficients. D is the diffusion constant of the particle, and zeta is the viscosity coefficients. So. I obtained these values with the Enskog formula. Yeah. So this is the amplifiers for the last plot. You see in this part, this law is a perfect fit, but divergence from this data behavior is remarkable. It's obvious. So. Mm-hmm. You see, I use applying it in the case with not very high densities. So in this case, the situation is that the theoretical predictions is agree with the simulation results. Yeah, not relative results. And but the problem is which one is correct? I mean, which one is exact? Because you see, in this case, this is already very close to the dilated regions. So you can also find a small divergence from this law. So maybe we can imagine that with at the very large time scale, you will the decay behavior will become logarithmic. So I mean the T2 minus 1 law might be not exact in this model. And then before I show the result of the current autocorrelation function, I explain why the calculation of this autocorrelation function is so difficult. It's very difficult because evolve a system, a period, we can obtain n pairs of Vt times V0 for calculation the velocity autocorrelation function. But if the system at some time, you can just obtain the one path of for calculation the current autocorrelation function, because the current is the sum of the local all of the particles. So in this case, if you want to obtain a smooth cover like the velocity autocorrelation function, you should apply 14 times of compute time to obtain such a small cover. So that is the reason why we never find the verification, the numerical verification to the power law of the energy current autocorrelation function. So this cover, I used 3 months with 100 CPU cluster, just for the single cover. I obtained such a time period for calculation. But the result is that in the dilute case, yeah, the theoretical prediction works very well. But with the increase of the density, you see this is not a very high density. It's indeed, it's still close to the dilute case. The deviation, obvious deviation occurs. The first character is that the polar, although the polar appears, but the polar becomes slower than the t2 minus 1. Yeah, both cases. Another feature is that there is a second stage of exponential decay. So these two kind of autocorrelation functions have big difference. And
what is the value of mu that corresponds to the phase transition?
0.7. 0.7.
0.7.
Yeah.
And you're at.
Yeah. And okay, let's continue our another result. So based on the mechanism I have not explained to you, I can obtain such a uniform formula for the autocorrelation function of velocity fluctuations. It looks like it gives in this formula. Here, the parameter D is still the parameter, the diffusion constant of particle diffusion. Well, d zeta is the diffusion constant of momentum diffusion. And for inverse, it gives in such a formula, you know. And all these values are calculated with the Untitled formula. In this case, you see in low density cases, this prediction, theoretical prediction, the results are perfectly agree with numerical simulations. But you know, I have emphasized here we apply the Untitled values. If we apply the Boltzmann equation, the result from Boltzmann equation, then you find a big difference. So in this case, it seems Untitled formula is correct for low densities. And then here is a result for what is, I will discuss what is the actually measured transport coefficient. What is the observed coefficients, I mean. So for in the case of velocity, in this plot, I show the direct result by tracing the target particles. By tracing target particles, we can obtain the mean square position as a function of time. You find in all these cases, you obtain it seems linear time-dependent relations. So it seems if we based on this figure, you can conclude that the motion of the target particle in two-dimensional gas is it's normal. It seems normal. It's Brownian. But this is not the diffusion constant. If you calculate the diffusion constant by this figure, then you obtain such a result, which means the the values will become saturation quickly, and then a slow decrease will occur. Evidence will appear, and in the high density case, the time-dependent future is more obvious. So this result is the observed result because we measure directly. On the other hand, we can apply the result of the correlation function, velocity autocorrelation function. I have just shown you, and you apply this result, you can calculate the diffusion constant by Green-Kubo formula. I mean, check the time in integral time at time tau, then you obtain such result. You see, this result has already put this peak and this result together. You find no difference. What means? That means the Green-Kubo formula is exactly agree with the direct measured results. The problem is in what extent this part will influence the measured result. I mean, because it is imperceptible, it is diverges in the thermodynamic limit, but the divergence is small, but the values up to macroscopic size is still small. So in that case, the influence can be ignored. But for the two-dimensional models, the result is that I will not discuss the detail of this figure, but the result is that for in this case, direct case, up to macroscopic size, you will obtain a 20% correction to the to these values. I mean, if we cut the integrate at the turning point. I mean, if I cut the integral here, then and compare the contribution of these two parts, then the tail will contribution to 20%, and with the increase of density, the contribution will become larger and larger. In this case, in the macroscopic size, the contribution already become dominant, becomes the my part of the diffusion constant. And in this case, even with the small system size we applied for numerical simulations, you find that the contribution become dominant. So the hydrodynamic tails usually cannot be ignored in this two-dimensional systems. But the situation there is different for thermal conductivity, because I have shown you that the decay of such a function is extended to a very large time scale, and it already decay to degree. So in this case, the contribution of the tail is relatively small. For example, in the direct case, the contribution is just 0% to the such as N-square values. But with the increase of the density, the contribution in this case, the contribution become dominant until macroscopic size. I mean, so relative, although they have the influence, but the influence is not so big as in this case in diffusion constant. And I will try to explain the difference we found in calculate the autocorrelation function of the current fluctuations. You apply such a formula because this is the sum of all the particles. Then, by consider the homogeneous of the system, then you obtain such a expression, which is n times these two terms, and these two terms. I'm sorry, this is a bar. The first term and the second term. The first term, what's this meaning of first term? The first term means the correlation between the target particle itself. And the second terms means the correlation between other the correlation of the target particle to other particles. And these two terms you can calculate respectively, and you find the first term decays as very similar to the to the manner of velocity correlation function. But this second term appears as a peak, a single peak functions. And these two, when you add these two parts to obtain the global Y, then it is possible to find to find such kind of stages. I mean, multi-stage decay should be induced by the second term. But the second time we are seldom focused to such a terms. And although this figure I want to show you is that the tail part should be also determined by the second term, because the first term is very similar to the velocity correlation function, which decays also in the high density case, which also decays faster than the T2 minus y. So it should not contribution such a slow decay, such a slow decay, because it's just more faster than the T minus y low. It seems I have what's the matter? It seems I have no time to explain the details, the mechanism. Indeed, maybe I can just show the results. Okay, thank you. To explain the mechanism, I need to stand the it's too big. I need to start the diffusion of the momentum initially carried by the target particle. I mean, the target particle initially carried the momentum, local currents, and other quantities. Then, by studying this, the relaxed process of these quantities, then we can explain. Maybe I can just show the result. Will you please? No, I don't think that will work. But, no, 不是。算了。Okay, yeah, this is the result. You see the diffusion of particles, the diffusion of the momentum, and the diffusion of the local currents. So in this way, you can obtain the diffusion behavior, which can be discovered by some formulas from some Gaussian functions, and use this result, you can you can test that the numerical result fits the predictions of this function, and also the relax of momentum of the central part, the central peak always such a low. So in this case, we can derive the decay behavior of the Power law, and in such a very simple way. But I think it is intuitive, and I obtained the exactly the same result reported previously, and it fits a numerical result. And also based on the same intuitive explanation, I obtained such a formula, such a uniform formula, which also works well. You have fun. Okay, that's the order of my talk. Thank you.